All right, let's start out with any questions.
That last one on the quiz would be nice to know. The second question.
Yep.
I know which problem it was emulating, but couldn't really figure out.
That's the wrong one. Very long annular cylinder. I think the difference between this and the textbook problem was that the textbook problem just used only letters.
Yeah.
So there we go. So problem 29 was the model.
So when we set up that integral, should it have been the smallest radius to that middle radius?
Let's see. Radius, so you're setting up, to find the electric field, you're doing a Gaussian cylinder. And what was your question again?
When you set up that integral, is it the inner radius to the middle radius? Like 0.18 to 0.21, I think are the numbers.
Yeah, if you're doing it by integration, yes.
Okay,
If you do it by Gauss's law, I think you avoid the integration.
yeah, you do. It's not the route I went.
You know, as with any problem, it's all the way your mind is working at that moment. Especially after if you've taken 3 other quizzes right before that. Did you want me to actually do it, or?
No, that's okay, I just figured it out.
Okay. Well, from what I've learned from G.I. Joe, knowing is half the battle.
Yeah.
I guess the other half is knowing it at the right time. Other questions? All right. All right, so let's finish up 26, and then we'll talk about the first test. So that you can have a smile like Stephanie did when she was leaving. Let's see, I'll put it that way. Work. So work is the integral of f dot d, I'm just make it a little bit more generic, dr. From the energy chapter from the first semester course. If this is conservative work, this is conservative force. I know that the force acting on an object is equal to some test charge times the electric field at the location of that test charge. Because that's the way they define electric field, so that would work. In essence, for the force that required two charges, the electric field requires one charge, so that one charge creates an electric field at some location where the second charge is. Multiply the electric field created by the first charge times the second charge, and you get the force on the second charge. So I probably could go slightly more specific. The force on charge 2 from charge 1 is equal to charge 2 times the electric field created by charge 1. Bringing this into my work equation up there, this is the integral of Q E dot dr. I can bring Q out because it's a constant for a particular problem. And because this is conservative work, I know that the conservative work being done based upon the work energy relationships is equal to the negative change in potential energy. And I guess specifically, since we are dealing with electric fields, this would be electric potential energy. Now, if I divide both sides by that test charge right there, I get this integral of E dot dr is equal to whatever the negative change in the potential energy is divided by the test charge. And that, we defined last time, or the time before that, as the negative change in electric potential. Oops, wrong letter. Electric potential. So we now have a relationship here between the potential and the electric field. And typically the minus sign goes with the integral. Typically it's written as the change in the electric potential is equal to the negative integral of E dot dr. So I'm just moving from one point in space to another point in space. That would be the change in R. Going through an electric field or a dot product, I find the change in potential. Let's find out if it works. It'd be nice if it does. And it's gonna be really nice if I can do this without actually screwing up a minus sign, because that's just the way I roll sometimes. So what I want to do is take a line of charge with some uniform linear charge density, so uniform linear charge density. And I have some point out here, a distance x away. And I first want to find the electric field at this point, then I want to find the electric potential at this point. Because I think before we did vertical line, I'm trying to remember what we did last time. I don't think I did this one. The electric field was done before, but I don't think we did the potential for that. Or I know we did it with just point charges, and I did the ring, and I did
linear, uniform, I've got uniform linear charge density. That's one of our notes that we had.
Alright. Okay, so it looks like what I did before was I had a uniform linear charge density here, and then I found the potential at this point.
Yes.
Okay, so it's a different orientation. I'm gonna set up some coordinate system here. And I hat, J hat. All right, so the electric field. Well, with either of them, whenever I have a charge distribution, I should not treat this like a point charge and plug straight into KQ over R squared. With a charge distribution, I need to come up with some differential. Some DQ here. And figure out what is the electric field or potential, whichever one I'm trying to solve for, at this point because of this differential. And then add up the infinite number of infinitesimally small charges, in other words, integrate. I don't have to come up with any temporary angles here, which is nice. So we end up with the electric field is generically K dq over R squared. I have two different variables in my formula right here, because dq is my differential, so it officially is a variable. And R is the distance from my point in question. What do we call this cleverly? Point P. Distance from point P to where my differential is, so this would be R. So I do need to come up with another temporary variable, which I'll call Z. And I'll let Z just be the distance from my vertical axis to where my differential is. Because linear charge density is charge divided by the length. I guess I just now established that the length of this is L. And that's also going to be equal to dq times dz. As the ratio of, if I take any section and the ratio of the charge to the length of that section is a constant, that's the uniform linear charge density. And since I've defined z to be this distance right here, then the width of that, the segment of charge has to have a length of dz. That is just powerful writing. Slightly better. So, I am going from, so K is a constant, this is Coulomb's constant, or the electrostatic constant, 1/4 pi epsilon sub naught. A reminder. So properly, probably with a subscript E or a subscript C. dq is equal to lambda dz. R is equal to x plus z squared. And now I have a single variable here, z. Lambda is a constant, so I can pull that out. So I've got, this is equal to k lambda dz over x plus z squared, and z is going from 0 to L. The smallest value of z is 0, and the largest value is the length of my uniform charge. So let's do a dramatic pause here for, are there any questions up to here? How do you solve it?
It's one of the ones that you give on tests, right? That interval?
Actually, this one's not there.
U sub?
Yeah, it's just a simple U substitution. So let U be x plus z, and du is equal to dx.
Is it dx or dz?
dz, sorry.
1 over minus, no, -1 over x plus z.
Yeah, that ultimately it's gonna be that. So I'll just jump straight to that. So that's k lambda, so the negative over x plus z from 0 to L. And so we get negative k lambda 1 over x plus L minus 1 over x, which is negative k lambda. Get common denominator, we end up with x minus x plus L over x plus L times x, which is, my numerator becomes negative L, and the negatives cancel out, so I'm left with k lambda L over x times x times x plus L. Alright, questions up to here before we talk about sort of what this means and then we solve the other one? So let's see if this makes any sense. I set up an I hat and a J hat right there. I really should throw in a direction. This should be I hat, I hat, I hat, I hat. If my linear charge density is positive, in other words, I've got this line of positive charge, and we know the electric field goes away from it, I would expect if this is positive, that my electric field would be positive. And if we come down here, K is a positive number, it's a constant. Lambda, if it's positive, is a positive number. L is a length, it is a positive number. X is the distance, it is also a positive number. So we end up with a positive value here. So if lambda is positive, my electric field is indeed in the positive I hat direction. If lambda is negative, it'll be in the negative I hat direction, which is what we would expect. So at least something went right. I have not screwed up the minus signs yet. Questions at the moment? So I'm gonna put that off to the side over here, because I suspect we might need to erase, but we'll find out. So my electric field at point B is K lambda L over X plus L. All right, so let's find the electric potential the old-fashioned way with calculus. And then we'll see if this is actually true. Well, it starts out very similar. I know that generically that V is equal to the integral of dq over r times k. I do need to establish one thing here. What do I need to establish? Let me ask you. Or I could make it an incredibly simple problem.
That infinitely far away is, or when your radius is infinitely far away, your voltage is zero.
Yeah, so if that's a classic, if I did not specify it, then you could just immediately go, oh, the potential is zero, because I'm gonna define that to be zero. However, we wanna do better than that. So if R is infinity, V is equal to zero. Just to establish, because remember, it was KQ over R plus some constant, and so this is establishing that constant to be zero. Similar type of things as we did before, we have now K integral of lambda dz over X plus Z from 0 to L. We'll pull the lambda out, so we've got lambda K integral 0 to L of dz over X plus Z. Do I need to put an I hat in here? Why not?
It's a scalar.
Yeah, all right. So, what is this integral? How do you solve it?
You substitution, then initial log X plus Z.
Wait, say it again?
Initial ln
Okay.
X plus Z.
Natural log.
Natural log, my bad.
Okay. So we end up with lambda K times the natural log of X plus Z from 0 to L. So we get lambda K times the natural log of X plus L minus natural log of X, which is lambda K natural log of x plus L over x. Which is lambda k times the natural log of, it depends on what form you want the final bit in, but I personally, L over x plus 1. Depends on what you like. So the question is, do these two equations obey this relationship here? Well, I hope so. It did earlier when I worked it out. All right, questions to hear before we actually do some integrating. All right, I do need room now. So that's just rewritten there, so I get that. How we got there. All right, so as I'm integrating here, it's E dot dr, and the question is, what exactly is dr? Well, this r is a vector from my charge to where this point is. So I have, what's my electric field? There it is. So I'm basically doing an integral, negative integral of k lambda L over x times x plus L I hat dot dr. Just want to, I suddenly had this sinking feeling that I was about to mess up the minus sign, as promised.